Building functions, exercises 2 and 3. So we're given two functions, f of x is equal to the quantity x minus 1 squared and g of x is equal to 3 minus x. So if we wanted to add f plus g, we would simply take f of x, which is x minus 1 squared, and then add 3 minus x. By foiling x minus 1 squared, we get x squared minus 2x plus 1, and then we tack on the end 3 minus x. Last step, just combine like terms, add up the x's, add up the constants, and we're left with x squared minus 3x plus 4. Okay? So f plus g equals x squared minus 3x plus 4. And that's pretty much it for the sum of two functions. So essentially, if I were to plug in a value for f of x and use that same value and plug it into g of x, and I added those two values, I would get the same thing if I took x equals that value and plugged it into the equation x squared minus 3x plus 4. So it's the properties of functions. So not only can we add functions, but if we wanted to, we could also subtract functions. So let's do f minus g. If I were to do f minus g, same thing, except now I'm going to put a minus sign in front of the function of g. So we're going to write x minus 1 squared minus the quantity 3 minus x. I'm going to distribute the negative sign through the parentheses, and that changes the sign. So now my positive 3 becomes negative 3, and my negative x becomes positive x. Expand the square, and then add like terms, and f minus g now equals x squared minus x minus 2. Last thing that we could do, I suppose, would be to maybe multiply the functions. So we could do f times g. But in every case, it's pretty much the same thing. We're going to do the math of the two functions, combine like terms to simplify, and that gives us what we call a composite function. It's a combination of two functions to get us one value. The math would work the same if I plugged in some value for x for both equations and then subtracted those values that I got, or if I made the two equations and I subtracted one equation from the other and plugged it in. It would be the same mathematically. So now let's do that f times g. And I don't want to write it that way. I'm going to say fg. So I'm going to take x minus 1 squared times 3 minus x. Now remember that when we expand our binomial, we'll get x squared minus 2x plus 1 times the quantity 3 minus x. This is pretty easy to do if I draw a grid. I'm just going to draw a 3 by 2 grid. So I'll say x squared minus 2x plus 1 on the top. Then on the bottom I'm going to say 3 minus x. And then you simply multiply the row times the columns. So x squared times 3 is 3x squared. Negative 2x times 3 is negative 6x. 3 times 1 is 3. Negative x times x squared is negative x cubed, and so on and so forth. Lastly, what I want to do is combine the like terms. So I have 1x cubed term, I have 2x squared terms, and I have 2x to the first terms. So I'm just going to simply add up the like terms to simplify my polynomial. So I'm going to add these two up, add those two up, and then my final answer is negative x cubed plus 5x squared minus 7x plus 3. And so that would be the function f times the function g. That's pretty much it. Again, I just want to remind everybody that what we're doing is, if I were to plug in a value, say, of 2 to both equations, and then whatever my answer was, I would get the same answer that I would expect if and we'll do an example of this later. If I were to multiply or add or subtract the values that I got that were yielded from the functions, and then it would be the same as if I plugged it into my composite function. So for problem number 3, same thing. I've got square root of x, and g of x is sine of x. When I add them up, there's really no way to simplify it. I just leave it as a square root of x plus sine of x. F minus g, same thing, square root of x minus sine of x. And when you multiply them, it's still the square root of x times sine of x. nothing really changes. I can't simplify or combine the square root of x with sine of x. There's no simplification. So we just kind of leave it the way it is, and then we plug in the value. So that was kind of an easy one. And sometimes it's that way. We're not always going to have like terms that we could simplify. We're not always going to do some fancy math trick. In this particular case, our composite function is just the combinations of the two functions, whether it be a product, a difference, or a sum. But from a computer programming standpoint, I can take one function that represents some sort of mathematical combination of two.